Welcome to a world where virtual wonders defy reality. A world where people, cars, and forests come to life with incredible details. These immersive and realistic looking scenes are created by Unreal Engine. Fueling this engine is an incredible technology that brings virtual world to life with stunningly accurate lights and shadows, making them look as real as can be. A technology that brings generational leap in computer graphics. This revolutionary technology is ray tracing. Ray tracing is the science of following a beam of light and understanding how it interacts with its surrounding objects. These interactions can include how light illuminates, reflects, or creates shadows, depending on the objects it falls on. The goal behind this is simple: to create realistic lighting and shadows that closely mimics the real world. This science is crucial to bring lifelike visual experiences in movies and games, evoking the emotions never felt before. Ray tracing applications were historically limited to big budget movie studios that could afford millions of dollars worth of CPU farms. These farms would typically have 35,000 CPU cores, and the rendering process would still take days to complete. Nvidia dedicated its efforts to laying the groundwork for ray tracing algorithms for nearly a decade, developing efficient algorithms that could trace millions of light rays and understand how they interacted within the virtual world. This video will discuss how ray tracing works in complex three-dimensional virtual world that is commonly used in development of movies, games, and virtual reality. How ray tracing is performed on millions of light rays using the revolutionary software algorithms. How Nvidia's RTX series of graphics cards use acceleration structures to speed up ray tracing processing. And how ray tracing workloads are processed at the hardware level, along with understanding the reason behind poor ray tracing performance on non-dedicated hardwares like Apple's M series of processors. I encourage you to watch the video till the end for a comprehensive understanding of ray tracing, the engineering behind ray tracing, and its processing on Nvidia's RTX series of graphics cards. What does ray tracing aim to solve? To answer this, we need to understand the development process behind movies and games. Most modern games like Battlefield, Counter-Strike, or Call of Duty are developed in a virtual three-dimensional environment. These virtual environments are created using objects, textures, and lighting effects. The dynamic nature of the three-dimensional environment enables the interactive nature of games, allowing players to explore virtual spaces, interact with different objects, and engage in a thrilling gameplay. These three-dimensional objects need to be transformed into two-dimensional scenes to be shown on our screens, which has previously been possible using a process called rasterization. Rasterization is the process of converting an image in a vector graphics format into a raster image, which is a series of pixels that can be displayed on a screen. Though rasterization has undergone extensive research and improvements over the years, it falls short in generating advanced effects that are necessary for realistic-looking scenes. These effects include reflections, refractions, shadows, atmospheric effects, and caustic effects, which collectively contribute to a realistic-looking visual. To maintain performance, these advanced effects are often approximated, compromising their quality. Ray tracing revolutionizes computer graphics by simulating the complex behavior of light rays found in the real world, leading to realistic-looking scenes. This scene looks real because of three important fundamental elements: the sun acting as the source of light rays, objects such as trees obstructing the rays, and the resulting formation of shadows. Ray tracing reproduces this scenario in a virtual world, accurately depicting the fine shadows made from the branches of the trees without the need for any approximations. This can get pretty intensive, as there can be thousands of light rays to be taken care of. Consider a scene with a light source, surfaces, and a camera. Ideally, the light rays would start from the source, hit the surfaces, and travel in the respective directions. These are the rays that contribute to image formation as they end up in the camera. To optimize resources, we concentrate on tracing these rays instead of all the rays in the scene. We could trace these rays starting from the light source, but we don't know which rays would end up in the camera. Hence, we start the tracing process from the camera and move into the scene, keeping track of the objects and the surfaces the ray encounters. To convert the scene into a 2D image, a flat surface with a 1920 by 1080 grid is placed in front of the camera. The intersection of the light rays with this surface plane forms a 2D image that is ultimately displayed on the computer screens. The true beauty behind tracing all of these rays lies in the software algorithms that perform such sophisticated ray traversals. These software algorithms are built using shaders. Shaders are special paint brushes that allows artists to create visual effects. These special paint brushes tells a computer to perform specific tasks on an object, like changing its shape, color, or how it appears on the screen. At the software level, the ray of light is generated using a ray generation shader. This shader acts as a manager for this ray, guiding the ray through the pixels on the surface plane and into the entire scene, keeping the track of the trajectory and the objects the ray encounters as it traverses the virtual world. When a ray intersects an object, the corresponding object's intersection shader is invoked. This shader calculates essential information such as intersection point, surface normal, texture coordinates, and other relevant properties associated with the object. Following the intersection, the anyHit shader is called to determine if the object is transparent using alpha testing. If the object is transparent, the ray continues with considerations for refraction. Since this is the first or the closest hit of the ray from its origin, the closest hit shader is invoked. This shader performs shading calculations and determines the final appearance of the surface at the point of intersection. It may also initiate additional rays such as refraction or reflection, depending on the object's properties. If the primary ray does not intersect any object, the miss shader is invoked. This shader defines the behavior of the ray when it misses all the objects, often setting the background color or simulating distant objects or the sky. These different shaders work together to determine the accurate color of the pixel on the surface, just like how an actual light ray would. We can shoot more rays to the same pixel to capture higher levels of details if needed. This process is applied to every pixel on the screen. For a full HD resolution, this would mean performing ray tracing for more than 2 million times. No doubt, ray tracing has historically been so slow. The ray traversal process and the ray triangle intersection process, which calculates the point of intersection, are the two most intensive processes in ray tracing. RTX algorithm optimizes these two processes using an acceleration structure called bounding volume hierarchy. Bounding volume hierarchy works by grouping objects in 3D scenes into bounding volumes or boxes based on their proximity. As an example, imagine a 3D box with three different objects: a sphere, a cube, and a tetrahedron representing our virtual world. This is the bounding volume hierarchy for our virtual world. Towards the right is a tree that represents the bounding volume hierarchy structure. The leaf node represents the bounding volumes of individual objects, and their parents represent the grouping by another bounding volume, all the way until the root node. The aim behind this hierarchical structure is to speed up ray traversal process using mathematical equations that are faster to perform than physically moving the ray in the three-dimensional world, and stop early if the ray does not intersect any object in the scene. This prevents us from performing the costly ray triangle intersection for each and every ray in the scene. Bounding volume hierarchy works by shooting a ray from a pixel. By comparing the coordinates of the ray with that of the bounding volume, we can determine if the ray would intersect the bounding volume or not. If the ray does intersect, like in this case, we perform the next check with the next set of bounding volumes on the tree in a similar fashion. Since this ray does not intersect any of the next bounding volumes, we can be sure that the ray will not intersect the underlying objects and simply assign the background color. This is how bounding volume hierarchy speeds up the ray traversal process. At the hardware level, Nvidia's RTX series of graphics cards feature dedicated hardware for accelerating bounding volume hierarchy traversal. These dedicated hardwares are ray tracing cores that allow extremely fast traversal of millions of rays. This is Turing, Nvidia's first GPU architecture designed to enable real-time ray tracing. And here is a simplified overview of the GPU die. It contains 6 graphics processing clusters, each containing several streaming multiprocessors that forms the heart of the GPU architecture. Each streaming multiprocessor handles integer and floating point instructions in these cores, as well as complex matrix calculations for deep learning models using the tensor cores. In addition to these capabilities, Turing introduces ray tracing cores. These cores are purpose-built to tackle the most challenging aspects of ray tracing workloads. The ray tracing cores have two essential components: the bounding intersection evaluators, designed specifically to perform ray traversal in three-dimensional virtual world by leveraging the bounding volume hierarchies, and the ray intersection evaluators that determine the exact point of intersection of a ray with an object. These two evaluators are the reason behind the real-time ray tracing in Nvidia's RTX series of graphics cards. Without the dedicated hardware-based evaluators, traversal of bounding volume hierarchies and ray triangle intersection relies on software-based implementations that compiles into thousands of lines of instructions. These instructions become a significant bottleneck for systems lacking specialized ray tracing hardware. For instance, Apple's M-series chips, which lack the dedicated ray tracing hardware, may experience significant slower performance compared to modern GPUs like Nvidia's Ada Lovelace architecture that features the improved ray tracing cores. This channel creates content on the engineering behind various technologies that transform the 21st century. If you are interested in important innovations and discoveries that left a lasting impact on humanity, please consider subscribing to the channel.